In this section 7.1, we take a look at the area of a region between two curves. And for the start, I just want to remind you of how to find the area under a curve. We talked about this last semester calculus, but it goes something like this. Recall that whenever f is positive, the area bounded by f of x, the function, the x-axis, and the lines x equals a and x equals b. So I've got some generic region where a is less than b, of course, just to create some spacing. The area is given by this definite integral from a to b of f of x dx. And by the fundamental theorem of calculus, I can say that that's capital F of b minus capital F of a. It's important to remember that capital F is the antiderivative of little f, or that the derivative of big F is little f, okay? So that's basically, where last semester calculus wrapped up. Here now, what we want to make sure we understand is that this gives us the area under f of x. And the important thing to note is that f of x has to be positive for this to happen, okay? Otherwise, we have to be very careful, and I'll talk about that a little bit later on in the video. Let's get a picture that corresponds to this formula here. So I'm going to sketch just some general function on my coordinate axis here. So here's, say, f of x from a to b. And then this green region is the region that I'm looking for. Okay, that's the region under the curve bounded by a, b, the x-axis, and the function. Okay, and what I'd like to do is I'd like to get some chunk or a slice of that area. The way you did this before was you cut that area up into a bunch of tiny pieces. You wrote down the sum of all the areas of those pieces, typically rectangles or trapezoids, and then you took a limit, and that limit got us to this definite integral. But in terms of the area, I still like to write down kind of a chunk of that, chunk of the overall area there. So I'm going to draw a little rectangle here, and I'm going to kind of center it at this point x f of x and give it some width dx. Okay, that width is going to be part of our formula for the area of that specific rectangle. So what I have here is dA, the area of that little rectangle there, and it's dA, it's going to represent the area of the entire green shaded region there. Okay, the area of that rectangle is the height of the rectangle, which is f of x, times the width dx, okay? And what we do, instead of adding all these up discretely, what we're able to do is take an integral, integrate dA, to find the area of the entire region. We integrate dA from a to b, and that's just integrating f of x dx, okay? So I'm going to give you kind of some tips and tricks and things that you should pay attention to when you're trying to find area bounded by one curve and eventually then two curves, and then setting us up so that we're able to take these areas and rotate them and revolve them around different axes and find volumes then. Okay, so let's do an example here. What I've got, I want to find the area bounded by f of x is 4 minus x squared in the first quadrant. Okay, so I've got some descriptors there that help me identify the region that I'm looking at. I'm going to sketch this here. So I get a coordinate axis, and I've got some tools, some knowledge from before that will help me graph this. I can find like some x and y intercepts. Y-intercept is easy. If I plug in 0 for x, 4 minus 0 squared is 4, I get the point 0, 4. I can also find x-intercepts relatively easy. First, I know that this is a quadratic, right? And I have a general idea of the behavior and the shape of a quadratic equation. It should be a parabola, right? To find the x-intercepts, I set the function equal to 0. I'm going to factor and solve and get both x values plus and minus 2. So on my x-axis, I'm going to mark where minus and plus 2 would be. And then I'm basically just going to sketch. Like I said, this should be parabolic. The minus in front of the x squared means it's opening downward. So I can just kind of sketch right on through. And I see this should be about the shape of my curve, of course. So what I'm looking at then is in the first quadrant, That's the positive x and y plane there. So I'm going to kind of box in my region with the bold white lines there. And then this orange spot is kind of what I'm looking. In the first quadrant, bounded by the x-axis, the y-axis, and the curve. Okay? So what I try to do now is figure out what integral I need to find that area. Okay, and I'm going to draw my rectangle again. I'm going to center it at a point x f of x. And f of x I know is 4 minus x squared. And I'm doing that so it helps me remember what the height of that point is. It depends on what x I choose. Of course, it's a function, right? Depends on which x I choose, but I have a formula for it. So I always know the height kind of that rectangle. And I'm going to box in around it here. It's got a width of dx. This shaded blue region is going to be my area of the representative element, or my dA. Okay? And for us, again, that's width times height. The width is dx, the height is f of x. So f of x times dx, but quickly I can replace f of x by what I know the height or the function to be. Okay? I'm ready to then find the area by integrating. So I'm going to integrate from the leftmost bound to the rightmost bound. And we see, because I'm in the first quadrant only, I'm going to integrate this dA from 0 to 2. Instead of from minus 2 to 2, the other value I found, I only care about the positive x-axis because I'm in the first quadrant. So I integrate from 0 to 2 the function 4 minus x squared dx. Okay? Integrating here is pretty straightforward. 4x minus x cubed over 3. Fundamental theorem of calculus says I evaluate this at 2 and then subtract what I get when I plug in 0. Since there's a 0 in every term of the antiderivative, I'm going to get nothing from that second part of the fundamental theorem. So really all I'm working with is what I get when I plug in 2. So that's 8 minus 8 thirds, or 16 thirds. Cool. So that's the area of that entire shaded region there. Okay. So what's kind of going on in the background here is I'm finding the area under the curve, of course, and we really kind of only think about this like there's one function involved. But what I'll try to argue to you in the next couple of examples is there really kind of two functions, the bottom function being the x-axis. And I never say much about it, but it's something that we have to pay attention to. In fact, I want to generalize this for having two curves. So let's say we have two curves, f of x and g of x, bounded by x equals a and x equals b, where a is less than b. So I'm just kind of making sure I have, going from left to right, from a to b. And then g of x is less than f of x. That's going to be an important thing to pay attention to. Which function is larger? Okay. Again, I want to sketch a rough picture of this. So I'm going to put my axes here. And I'm going to sketch some generic f function and some generic g function between a and b. So then the shaded region I'm looking at is bounded by those four colored pieces there. A, B, F, and G. Okay? So it doesn't really matter what F and G are doing here. If they intersect at any point, we have to be careful. We'll talk about that a little later. But in general, if F is always bigger than G on the interval from A to B, then I have a general picture like this. Okay? So I want to try to kind of find a representative element of the area. And to do that, I need to kind of talk about some distances here. Any distance from the x-axis up to f of x has a height of f of x. So what I do here is I'm just going to sketch some random lines here up to my function f of x. All of those guys have a height of f. It depends on the x that I choose, right? It depends on where I'm at on the x-axis when I go up to that function f of x, how high it is. But f of x will give me that height. I want you to try to remember that. Same idea with g of x. If I go from the x-axis up to g, that has a height of g of x. What I want is in between the two. I want that green line there. I want that height because that's going to be the height of my representative element that I'm going to integrate over. That height will change as I move throughout my region here, but the formula for it will basically stay the same. Again, depending on which x I choose gives me different heights for f and g, but the formula should work for any x that I choose. Okay, in fact, all x's in that region. So this guy is actually f of x minus g of x. And I want you to try to convince yourself of that. From the x-axis up to f is f. From the x-axis up to g is g. I want the remainder of those two. So I take the tallest one, f, and I subtract the shortest one, g. I get f minus g. That also works in the region where g falls below the x-axis down in here. Okay, g is negative there, so when I subtract it, I'm actually adding some height, which makes sense because I've got more than the height of f in that little region. Okay, so f minus g should almost always work when we're doing these things. There's some highlights that we need to pay attention to. Okay, so my representative area of the region, my little slice, would have a height of f minus g. Okay, I'm going to draw that here. There's my representative element, dx. The height is f minus g. Even over there, right? I've shifted things a little bit. The x's are different over to the left there, but the heights are still given by the functions, the top one minus the bottom one. And I'm going to use that all the time, top minus bottom. Okay, so my area is in the integral from a to b of f of x minus g of x dx. And again, I often think about this as the integral of the top function minus the bottom function. Okay. Let's apply this in some examples. I want you to see how kind of things break apart. I'm going to do 2 or 3 examples here. The first is going to be just cosine of x. Find the area bounded by cosine of x, the x-axis, x equals 0, and x equals pi over 2. Okay. This is going to feel kind of like the first example I did. This is going to feel very much like the generic integral of f of x, but I want you to try to think about it as there's being 2 curves. Okay, I'm going to put the graph of cosine of x in here so I don't have to sketch it. So there it is. I've got cosine of x, and I've actually plotted the points when x is 0 and x is pi over 2. So those are some nice values there. That's why I chose them. And I'm going to highlight kind of my region here. X equals 0 is this blue line, the vertical line. X equals pi over 2 is that point there. That's where I'm stopping on the right. That's like my B. Cosine of x is, of course, that curve in red. And the x-axis is really my g of x. The x-axis, when y is 0, y equals 0, that's the bottom part of my region. So I'm going to shade in then this representative element here, and the yellow area then is the area that I want. I'm going to use the green area in that rectangle to help me figure out what the area of the entire region is. Okay? Again, that region has a width of dx, and the height is going to be cosine of x. That should make sense from what we talked about before, right? It's just the height of the function. But I want you to think about taking away the bottom function. It seems redundant because I'm not taking away anything. But as soon as I change the x-axis, say if I wanted to find the area bounded by instead y equals 1, now I have some area, some height to take away. So when I try to think about there being 2 curves, that helps when things change. And actually, I see more explicitly what those 2 curves are. In this case, it really is the function, the top function, f of x, minus the bottom function, y equals 0. Okay? So that f minus g is going to be what goes inside the height, or what goes inside my integral. Again, top minus bottom. So my area is the integral from pi over 2, from 0 to pi over 2 of cosine of x minus 0 dx. Again, that 0 doesn't really need to be there. I can just say cosine of x. That's fine. But I'm trying to make a point. When I integrate, antiderivative of cosine of x is sine of x. Evaluate from 0 to pi over 2. I'm sorry, I'm going a little fast. Let's go back a little bit. Which I get sine of x, like I said, Plug in pi over 2. Sine of pi over 2 is 1. Minus sine of 0 is 0. So all in total, that yellow shaded region should give me a value of 1, which is pretty cool. You see the what if. I've already skipped ahead a little bit. I apologize. I'm going to change things a little bit here. I'm going to work on a similar example, but I'm going to change. I'm going to say, what if we change the bounds to x equals pi over 2 and x equals 3 pi over 2? So if you go back a little bit, you'll see that picture. I've stopped it at pi over 2, right? You don't see any more of the cosine function. So I'm going to have to zoom out a little bit, and I'm going to give you another picture here. Cosine from pi over 2 to 3 pi over 2. That's what I'm working with. And that black line right in the middle is the x-axis, right? So my function is actually below the x-axis. And this example here is why I was making such a big deal about having two functions, okay? When I try to find this area, again, I'm gonna highlight my bounds here, the region that I'm looking at. My function is cosine of x. G of x is still 0. It's the x-axis, okay? So I've got my shaded region there, and I've highlighted the x-axis as like my g function, okay? Now my representative area, dx, there is the width, the height. We have to be careful. This isn't really just cosine of x anymore, right? If I think about that height as being kind of a positive height, then what I'm going to want to do is take the top function, 0, minus the bottom function, cosine of x. And the important thing to try to remember here is that cosine of x in this region is negative, okay? Cosine of x is negative on this interval. So 0 minus cosine is actually positive, right? 0 minus a negative number is a positive number. So what I should be getting from this is a positive area. Negative area doesn't make all that much sense. We can talk about it kind of abstractly. But when we go through this calculation to find this area, we have to know how to write the integral down so that it gives us the area that we want. I can't just do integral of cosine from pi over 2 to 3 pi over 2. I have to be careful. I have to do the top function minus the bottom function. And we don't typically think about the x-axis as being some function, but I have to kind of label it that way so I make sure I get the area the correct way. Okay, so my area is from pi over 2 to 3 pi over 2. The height of that region is 0 minus cosine of x. And everything should come out positive then. When I take the antiderivative, I'm taking the antiderivative of a minus cosine. Antiderivative of minus cosine. What derivative do I take to get minus cosine? That should be a minus sine. Oh, I'm sorry. I want to make a point here that top minus bottom isn't necessarily f minus g. So the formula said I take f and I subtract g. F and g are just names. They're names of the functions. What I really need is top minus bottom, okay? So that's a kind of deceiving thing. We think it's the formula. That formula should work for everything. We have to know which function is larger. Again, that formula was only good as long as f is bigger than g. That's obviously not the case here because g, 0, is bigger than cosine in that interval, right? So again, back to the antiderivative. My area should be minus sine, plug in 3 pi over 2 and pi over 2, okay? When I plug in 3 pi over 2, I get a minus 1. When I plug in a pi over 2, I get a 1. But fundamental theorem of calculus says I subtract those. So I get a minus 1 is a minus 2 times the negative out front there is a positive 2. Positive area, okay? Area between those two regions is positive. It's 2 units. Let's do one more example. Things are slightly different here. Find the area of the region bounded by sine of x, I like trig here, y equals 3, x equals 0, and x equals pi. So I've kind of explicitly given, 4 different pieces that should make up my region here. So let's draw a picture. I'm gonna insert one. What does sine of x look like? And I've got this guy here. So there's sine of x, and I've given a little bit of a window to it. I also have y equals 3 kind of colored in blue there. I'm going to color over it in a second. So I'm going to trace all these four things here. I've got sine of x. I've got y equals 3. I've got x equals 0. It's in blue there. And x equals pi. We don't have a nice point for, but there it is. It's in purple. So that kind of boxed in area is what I'm looking for. I'm going to shade that all in. That's what I want. Try to color it in really good. Okay. So again, I'm going to try to draw that representative element, that little rectangle. I can put it pretty much wherever in here. I'm going to shade it in green. I need to know the width, dx, of course. That's pretty much the trend here. And I need to know the height of that guy. And again, try to think top minus bottom. We'll get back to that. I can go kind of right to saying top minus bottom, but I want you to try to remember what heights are going on. Up to sine of x, the height is sine of x. Up to 3, the height is 3. Okay? I want what's in between. I want the height of that green rectangle. So I don't do just sine of x. I've got to do the larger area, 3, the larger height, 3, minus the smaller height, sine of x. Okay, top minus bottom. So when I set up my integral, when I find the area, it's the integral from 0 to pi of 3 minus sine x dx. Integrate each of those with respect to x. I get 3x plus cosine, right? Derivative of cosine is a minus sine, so that checks out. Plug in pi. I get 3 pi minus 1, and subtract what I get when I plug in 0. 0 plus 1. Cosine of 0 is 1. So this all breaks down to 3 pi minus 2. Okay? So, area between two curves, top minus bottom. In the next video, I'm going to talk a little bit about what happens if we've got functions described as functions of y instead of functions of x. Things will be very similar, but they're going to rotate about 90 degrees. Okay, it's really not too hard to handle. Really similar formula, similar shapes. And just as a little aside, 3 pi minus 2, just make sure that's positive and that makes sense. 3 times pi is what? It's 3 times something a little bit bigger than 3, so that's a little bit bigger than 9. Minus 2 is something a little bigger than 7. Cool. So it's a positive area. Things are hopefully making sense here. I think I'm going to do another example, quick video, just a couple minutes long, where I go through a more complicated set of functions that we find the area between. Other than that, thanks for watching.